Okay, so it's my pleasure to have Professor Ujue Tayo. No, I'm just Professor Ujue Tayo from CUNEF Universidad. As we tried to have Ujue in Brazil 2 years ago, but there were some complications. Now she finally came here for the first time, and she will give us a talk about the eigenfunctions of the Laplace-Beltrame operator and random points. Ujue?
Okay, thank you very much. Yeah, thank you for saying my name with Carioca accent. That's the first time in my life. Thank you. So thank you, Mateus. Thank you, Felipe, wherever he is. And thank you also to Emmanuel in the distance, I guess. Yeah. Okay, thank you to the organizers. It's my first time at IMPA. Yeah. It's actually my first time at Rio de Janeiro. It's my first time in Brazil. And even more, it's my first time in South America, which is crucial because I have family in Argentina. So after this talk, most likely I will be disinherited of my family, and I had committed a big crime coming before to Brazil, to Argentina. But still, let's do some mathematics and make it worth it. I'm gonna talk about this. Yeah, sure.
Brazil 1, Argentina 0.
Yeah, which is good for you, but for me, yeah. All right. So I'm going to be speaking about this relationship between eigenfunctions of the Laplace-Beltrame operator and some very specific random set of points that are called determinantal point processes. So we are going to be working on compact manifolds during this talk. For some of the results, we have extensions to other places, but most likely we will fix into compact manifolds. Okay, so what's the motivation we have in here? Of course, I will go into the proper definitions of determinantal point processes, but for those of you that already know them, I will give you just a hint. Determinantal point processes are random point processes on manifolds in this case that capture the geometry somehow of the manifold while respecting some minimal distance between points. So there are point processes that exhibit some kind of repulsion among the points. Then we have these Laplace-Beltrame eigenfunctions. When we have a compact manifold, we can define a Laplace-Beltrame operator, and then the L2 space of functions on this compact manifold can be decomposed in a basis. So we have a basis of L2 that is just a direct sum of eigenfunctions of the Laplace-Beltrame operator. And this allows us to do some kind of Fourier analysis right there. I hope you agree, because that's the Fourier thing that I have on my slides, right? So we are going to do Fourier analysis on compact manifolds using the eigenfunctions of the Laplace-Beltrame operator. Okay, and at the end of the day, we have random points. There are good random points. And the question is, in which sense they are good, right? So we will go to different numerical tags. We have already seen some of them today with Dima's talk. Okay, actually, Dimas, you made the perfect introduction for my talk, so I hope not to repeat too many things. So let's start with this equidistributed points on manifolds, right? I will explain you why I study points on manifolds, what are determinantal point processes, some few notes about the Laplace-Beltrame spectrum on manifolds, and then I will go to the main topic of this talk, that is, I have a determinantal point process, I can build it based on some functions, and these functions are going to be the Laplace-Beltrame eigenfunctions, right? And this is going to be called the harmonic ensemble. We will go through it. And then a lot of conclusions, future work, ongoing work, etc. Okay, so motivation for study points on places. Now, this is maybe a bit personal, but in a world of well-distributed points, as the pictures, we don't need to give definitions. So Dima already passed through this idea. If we are working on the circle, the sphere of dimension 1, and I ask you to give me 5 well-distributed points, I hope everybody on the audience talk about the 5 roots of unity, right? Or if you prefer, you take a regular pentagon and you pick the vertices up to a random face, of course, right? But this happens still if I ask you for 17 well-distributed points on the circle, right? We always have like a natural, at least a natural thought that the roots of unity are going to be well-distributed in any sense. We can think of the same type of question when we pick the hexagonal lattice on the plane. Okay, hexagonal lattice should be optimal for everything, and I said they should because it's this very big Kuhn-Kummer conjecture, right, of universal optimality, but at least this is a natural candidate when trying to solve any of those distribution problems on places. And that's the only place where we are going to check the plane because we will be working on compact from now on. All right, but when we go to the sphere of dimension 2, then things start not to behave as well as before. Okay, why? Well, there are different reasons, but if we were working on the circle, then for any n natural number, we have a regular polygon with n vertices, right? And that's the natural candidates. How many polyhedron are there, regular polyhedron in general? We only have the Platonic solids, right? So we lose this kind of natural candidates. If I ask him for the 5 points on the sphere that appear on the previous talk, this problem was solved partially, not even 10 years ago, kind of. So it's a really difficult problem. If you want to distribute 7 points on the sphere, you have to give a very concrete and proper definition of what well-distributed points means, okay? And the answers are going to differ. Also, if we look, if we approach the sphere locally, we will find a plane, and we can think of the hexagonal lattice on the plane and then glue it to the sphere. But then we have the characteristic of the sphere, which is of course different of the plane, and then we can't have just hexagons, right? We have to add some pentagons, football, soccer, blah, blah, blah. Okay, so what are well-distributed points? There are many definitions, and this is where my personal taste came into play. So we have points associated with packing problems. We also checked them on the previous talk. So you can think of a packing problem on the sphere of dimension 2. You just have to place some spherical caps on the sphere of dimension 2, and you have to follow 2 rules. So no overlapping is permitted. So we have to be empty intersection, and the radius of every empty cap has to be the same. And then the question would be, where should I place my spherical caps such that the radius is as big as possible? Okay, that's a packing problem on the sphere. Of course, then you can go and take the center of the spherical caps, and you have somehow well-distributed points. Nice. This is a max-min problem, and there are hundreds of max-min problems, not only in the sphere, but in any manifold. Then we have points that are good interpolation nodes, and there we go again to Dima's talk, to the concept of spherical design, right? Where we can approximate the integral of a polynomial, any polynomial on the sphere, up to degree t, by just the sum of the polynomial evaluated on my points, my set of nodes on the sphere, right? The dimension of the polynomial is t, and we talk about t designs, so they interpolate perfectly up to degree t, and those points are also nicely distributed points in the sphere, of course. Repulsive potentials. Again, I think it was Thomson's problem, the one that appears in Dima's talk. You know, Thomson's problem has this, so it comes from physics, like almost every repulsive potential that we work with, right? And Thomson was known for being the discoverer, or the one who gave the definition of the electron. And he proposed this atomic model where atoms were spheres, were balls. And then the positive charge of the atom was inside the ball, and all the negative charge was on the surface, so on the sphere of dimension 2. And the question was, given a number of electrons, 5 electrons, 6 electrons, small numbers, where do the electrons find the equilibrium state, right? So when the electrostatic potential is minimized, where are they located? Okay, so this is still an open problem for most of the cases. And again, if we go to the sphere of dimension 1, then points that satisfy the packing problem, T designs, points that minimize most of the repulsive potentials are the roots of unity, right? We have a unique solution for every single one of these definitions. But if we go to the sphere of dimension 2, then things get trickier. And then we have points that solve packing problems that do not solve problems of minimizing potential. Then we have good interpolation nodes that are quite close, and then they are not good for packing problems, et cetera, et cetera. So actually, most of the results on this field are just theorems of implications, stating things like if we have a T designed and we have this extra condition, then those points minimize this potential. Or if we have points that minimize this potential, then they are also solving this type of packing problems, right? And this is just for the sphere of dimension 2, which is kind of the most easy manifold to work with. Okay, so now you have to think of these problems, but go out of the sphere of dimension 2, and we go on higher dimensions. We lose this perfect symmetry thing of the sphere, and we start working with more abstract thing and more difficult manifolds. Okay, for the purpose of today's talk, I'm gonna give you 2 definitions, and I will be working with these 2 definitions. The first one already appeared, is there is energy. So we can define on any manifold, given a metric there, so compact manifolds, Riemannian manifolds. Okay, the risk S energy of a set of points that I will call omega n is given by this sum. Okay, we sum the inverse of the distance between points up to a certain power s. In general, we can define s to be any real number. For the purpose of this talk, I will stick with positive s, and so I'm going to worry only about the problem of minimizing. Whenever, of course, you have negative s, you can think of the problem of maximizing. This is the maximizing distance problem. All right. So in general, minimizing this risk energy yields well-spaced configurations. So we can say points are well distributed. Still, this is not super general, and we have to worry about the concrete manifold and the concrete metric we are considering on the manifold. And the problem is that if we start trying to solve this problem on a deterministic way, it's almost impossible. So for instance, if you try to minimize this potential for s equal 2 and n equals 7, it is an open problem, right? And it's easy, 7 points, sphere, okay, and we just have the sum of the inverse of the distance square, and it is an open problem. Just go for larger s, smaller s, et cetera, and it's getting more and more complicated, right? Just let me say a little note about the first point there. If you have 2 points that are really close on your manifold, then of course the distance is going to be small. And then we have the distance that is a small number up to an exponent s. You have different behaviors when s belongs to the interval 0, 1, and when it belongs to 1, whatever, infinity, okay? But in any case, we have a small number up to some exponent that it's making it smaller, and then we have 1 over this. So this quantity is going to be really big. That's why it yields into well-separated configurations, right? It's a naturally repulsive potential. Okay. Now, another really interesting thing here is to worry about how does the number s affect into the local or global behavior of the point configurations, right? For instance, when we have s going to infinity, then we obtain again the terms problem as appeared in the first talk. That means when s is really big, then if I'm trying to minimize this quantity, I can't allow 2 points to be really close, because this is going to explode, because s is going to infinity, right? So I need every single one of these distances to be as big as possible. And this is a max-min problem, so this is a packing problem, and this is a theorem. And I said it roughly, and then you need a proper proof, right? But there is a theorem that states that solution of these problems when s goes to infinity are solution for the best packing problem, right? So there are different relations between one and another. What happens if s is small? Let's think on the sphere again, and s between 0 and 1. Then maybe we can allow 2 points to be closer than in a packing problem solution, but the global behavior has to be really nice, right? So they have to mimic the uniform distribution in a really, really perfect way. Okay, so there are different things, and it's all depending on this parameter S, of course, on the manifold we are working with. All right, this is the second one, the discrepancy. And for discrepancy, instead of thinking of concrete configurations of endpoints, we are going to be working with sequences of configurations, because we are only going to worry about the asymptotic expansion, asymptotic behavior of the discrepancy. Okay, so now, for any natural number n, I have a set omega n of endpoints on the manifolds, and they don't have to be related. I mean, I can take, let's go to the sphere. The first element is a configuration of 1 point, whatever, then 2 points, then 3 points, and the 2 and the 3 points don't have to be the same. Okay, they have to be completely defined on a different way. Okay, so once I have my sequence of configurations and points, that in this field is called a family of points, then what I'm going to compare is the number of points that fall into a set. Actually, it's going to be a family of sets with the volume of this set. Okay, and I'm going to take a norm over this quantity. Let's go and do some example again. Just imagine that my family of test sets, that here is with this calligraphical A, are the hemispheres on the sphere of dimension 2. Okay, if I want to prove that a family of points is well distributed, then if I take one hemisphere, it should contain half of the points, right? But if you take another hemisphere, it should contain half of the points, and so on. Okay, so that's what discrepancy is doing. But usually we don't take hemispheres, we take a larger family of sets, but still that would be the idea. And then I have to compare all of my hemispheres, and I can compare them using different norms. I can use the L2 norm, I can use the L1 norm, but here I will be using the supremum norm, the L infinity. So I just take the supremum of these quantities, right? Of course, if you have an odd number of points, you won't have half of the points in any hemisphere, right? So the discrepancy is never going to be 0. But if you have an even number of points, also the discrepancy is not going to be 0, unless you have 2 points. All right, so this is the second one. And for this quantity, I'm not worried about what's the value of the discrepancy for a concrete number of points, but how does the discrepancy grow when the number of points goes to infinity? Whenever I have a sequence of configurations and points, a family of points that tends to the uniform measure, the discrepancy is going to tend to 0. But I wonder how fast. Okay, so what I'm going to check is how fast the discrepancy is going to go to 0. Okay, a couple of notes, just in case. Yeah, I will be writing little notes on my slides, just in case somebody has worked with some of those things, just to ring a bell, but they are not necessary to follow the talk, right? The first one is that the L2 discrepancy, instead of taking here the supremum, I average the L2 norm between all the different spherical caps, or the test set that I have. This is related to the -1 risk energy through the Stolarski invariance formula. So again, we have a relation between two different definitions. So points with minimal discrepancy, they have a very particular risk -1 energy. Second one, L2 discrepancy is related to quasi-Monte Carlo methods. So you know, when you don't want to do some integrals because your manifold is ugly, and then you go with Monte Carlo methods, right? And you just sum some function on some points, you can do better if you take those points to have small discrepancy in this sense, right? The L2 discrepancy. And then those points are called quasi-Monte Carlo methods. And then if you use those points, then you obtain less error on integration methods. All right. So that's my motivation for studying sets of points, part of my motivation. And now let's go into random processes. I'm not going to, sure. Oh, it has to be measurable and Borel semi-continuous. So you have to add some, of course, yeah. I'm not giving all of the adjectives, but yeah, Borel semi-continuous, yeah. Okay, So again, I'm not going to give the definition of a random point process because we don't need it for this talk. We can think for the moment, for this half an hour, that a point process is a random discrete subset of my manifold. And that's enough, right? So if with a random variable, I will take 1 point of my manifold, with a random process, I will take n points at the same time of my manifold. All right, we have different examples of point processes. Those are some words that that always appear, and we will have to go through them. As well as for random variables, we have these so-called density functions that help us a lot, right? When we want to compute specific numbers, if we want to compute the expected value of a function of my random variable, then it's really great to have a density function. Otherwise, okay. So we have more than that. Here, when we are working with random processes, we have the intensity functions, we have the correlation functions, and we have the void probabilities, among others. We will go through them, okay? But we have some key functions that will help us doing some computations. Okay, so here's some examples. This is a Poisson point process. Nice, the sphere of, the square of dimension 2. And then we have those points that for any of our purposes, discrepancy or minimizing the risk energy are clearly badly distributed. Why? Because I can find pairs of points that are really close to each other. Okay, and why so? This is because Poisson point processes are independent. So I can sample 1 point and then I can sample another point, it can be really close. And by the way, this is also happening with the uniform points. Okay, if I sample from the uniform distribution on the sphere, and I compute the associated risk energy of points coming from the uniform distribution, this is not going to be good. And it's not going to be good because this can happen. I can have 2 points as close as I want to. Gibbs processes are nice because they have some relation. They are not independent, and I can control this relationship with this thing that I call here R-mean, but they are difficult to work with. And determinantal point processes, that are the ones that we are going to study, they show this natural repulsion. Okay, so for any point sampled for a determinantal point process, there is a radius, depending of course on the manifold and on the number of points that are sampling, for which with probability 0, or with probability 1, I won't find another point on its radius, right? With the geodesic pole along the point. Okay, so correlation functions. We need to do some mathematics here. Correlation functions, again, not given the proper definition, but this is a proposition. I should have written here proposition. That's how we can use correlation functions. As well as for density functions on random variables, we have this type of formula, right, where we take any measurable function, and then the expected value of a function evaluated on my random variable can be computed using the density function. Here, for a point process of n points, I have n different pair correlation functions, and then the expected value of points following my distribution of the sum among all different k-tuples of this measurable function can be computed through one integral, which is nice, okay? This is helping a lot, because then I just have to multiply the function evaluated on these k variables against this correlation function, and the number is going to be what I want. Okay, so those are correlation functions. And what are determinantal point processes? Okay, so there are simple point processes for which I need to have a kernel. So this is one of the slides where I can work further than in just compact manifolds. And we can take any lambda space that is locally compact and Polish. Polish is separable, completely metrizable space. Okay, and of course, probability, I'm taking a radon measure, okay? And then I take a kernel. The kernel can go into the complex numbers or into the real numbers. Here you choose your one, the one that you prefer, okay? And then a point process is called determinantal if it has correlation functions, which is not always the case. It has to have correlation functions, and then the correlation functions follow this definition here. So every correlation function is going to be the determinant of a matrix whose entries are just the kernel evaluated on the different combinations of pairs of points, right? So this particular shape, this is a determinantal point process. Okay, so here again we have the definition. Now I'm thinking already on manifolds. If we consider the first one, the first correlation function, this is the determinant of a 1 times 1 matrix. Okay, so the only entry that my matrix has is this k of xx, and it is the density. Okay, this is the density of the point process. And if we start thinking about these problems of distributing points, and I want the points to be well distributed, I would love this first intensity function of the first correlation function to be constant, right? Because otherwise, depending on the point I'm choosing, is taking a different value. So it's having different density. The function, the process will have different density depending on which point I'm looking at. Okay, the second one, and again, this is for people working with some probability stuff, otherwise forget about it. The pair correlation tells me it's on the definition, right? What's the relation between every 2 points? And it's computed by this formula. We have the radius and we have the first correlation function square, and it's less than 1, always for determinantal point processes. And that means that the process is repulsive. When we have a process that is repulsive, then we can always find a neighborhood of a point with no other point of the process, okay, with probability 1. Nice. And then, if we consider the second correlation function, we can come up with this really nice formula. It's just the formula I gave you before, but for 2, right? For k equal 2. Then, if I take the expected value of the sum of a function on just 2 points, second correlation functions, is going to be the integral on the manifold times the manifold. This is the determinant of a 2 times 2 matrix whose entries are the kernel, right? And then I have here just the function that I'm thinking. So please start thinking of the Riest energies, because they are functions that only care about 2 different points. And you can start thinking, okay, I can plug in here my formula, and this is going to be reduced to compute an integral, which is, of course, not easy in most of the cases. But then maybe I can look for nice kernels, and maybe I can compute some expected value of Riest energies on random points on an easy way. Okay, so the determinant structure excludes configurations with closed points. We just check it with the pair correlation. Where was it stated? I should say physicists were the first one stating determinantal point processes properly. So they came on fermions out those particles that have some kind of repulsion among them that is perfectly modelized by the determinantal point process. So physicists working on fermionic statistics are always working with determinantal point processes. But it also arises on random matrix theory, which is quite nice. So I don't know if you're familiar with random matrix theory. If not, you just think of a matrix with random entries, and then you force the matrix to have some symmetry on the distribution. For example, I'm going to take an Hermitian matrices, plug in every entry independent Gaussian random values, right? But then I force the probability of the matrix not to change if I multiply by a unitary matrix or by an orthogonal matrix or whatever. So I force some symmetry on the distribution. Okay, if you have this, such a thing is a random matrix. And if you have this, and then you compute the eigenvalues of the random matrix, you obtain some points. If the matrix is symmetric, real points. If the matrix is non-symmetric, Hermitian, or whatever, complex points. Those points that you obtain, that are whether real or complex, are points obtained by a determinantal point process. So you can write specifically any probability, any distribution of those points coming from random matrix theory using determinantal point processes. Okay. And And we have a very particular, let us forget about probability for a moment, and let's go back to, I don't know, linear algebra. Whenever we have a subspace of finite dimension, then we can consider a basis of this subspace, and then we can define this, then we can define this kernel, that is just the projection kernel, that is why I write P here, of the general space into my subspace, right? So I just take a basis, orthonormal basis, otherwise I add here some numbers and that's enough, and then I have this kernel. This is a reproducing kernel, right? This is the whole theory of reproducing kernel Hilbert spaces. In the easiest case, because here I'm taking a subspace of finite dimensional. We can do that with any Hilbert space with infinite dimension. Okay, so we can start thinking about these projection kernels and trying to build the terminal point process with projection kernels. Why not? Okay, and this is a corollary of a general theorem that is due to Mackey and Shosnikov, not together. So Odile Mackey wrote it, and then Alexander Shosnikov wrote it, and apparently it was the same theorem, stated on really different words. Okay, but the corollary of the general theorem would be the following one. We just consider the space of L2 functions of my manifold, and then I take a subspace of this space L2 of finite dimension n. Okay, and then I consider the projection kernel, also of the subspace L2 into my little subspace that I just choose of finite dimension, and this is given rise to a determinantal point process always. And not only there exists such a thing, but we can sample these things. So we can make a program on the computer and get some points for this particular kernel, right? So this is, everything is completely explicit. Also, in terms of complexity, not the best. But still, sampling from the uniform distribution in terms of complexity is also not the best, right? If you want to sample n points. So the complexity is the same as the one from sampling for uniform distribution. Yeah, and we can talk about it later. Yeah. Okay, so let's go back to my risk energy. Here again, the distribution, the definition. And now, of course, you have already had time to think about it. If I want to compute the expected value of the risk energy of some random points, then the only thing I need to compute is those things here, right? Whenever they are coming from a determinantal point process. All right, for the discrepancy, we are not so lucky, okay? We can do that whenever we want to, whenever we have the sum of a function that is measurable, but then discrepancy doesn't have such an expression. So in general, there is not a strategy for computing the discrepancy of points coming from determinantal point processes. Still, it's been done for a lot of cases. But for every case, you have to go with a specific trick that the manifold had, or the point have, or the harmonic part of the Laplacian operator has. Okay, just in case you are interested in this topic of determinantal point processes, I have here a couple of books. The one on the right is, I think, the only book written on determinantal point process. Correct me if you know another one, right? And the comment that I had from people that have read it, I have read it, but the comment that I have most is that it's written for people from probability, working in probability, and then the proofs that need some analysis are really developed, and you may think, oh, that's easy, but they are step by step, and then the proofs that are based on probability, maybe they are not so developed. So I had to learn a lot of probability to do the exercise of this book. And the other one is this Random Matrices by Mehta. Really nice book, really well written. It's using the word determinantal point processes just a few times, but most of the processes that appear there are determinantal, and he's computing explicitly the kernels, and he's working on those things. And it's really nice. It's such a nice book. Okay, so let's go back to the other part. We have the Laplace-Beltrami operator, just definition in case you're not used to it. Okay, the minus, I take the minus sign. This is okay. I think this is not always the case. So for me, this Laplace-Beltrami operator goes with the minus. The divergence of the gradient. Of course, now I'm working on a Riemannian manifold compact, okay, with a metric. You know, you have a lot of properties with this operator, is self-adjoint. The eigenvalues are real, and we can order them starting from 0, which is nice. And then the eigenfunctions, I've already mentioned, form an orthonormal basis of L2 of the manifold. Perfect. Okay, then we have the Weil's law, which is super cool. Why? Because it allows us to give a track of how big the eigenvalues are going, right? So essentially, if we consider an upper bound that I call this capital lambda, then the number of eigenvalues that are smaller than this one, remember eigenvalues here are positive and start from 0, so real and start from 0, is going to be approximately like this upper bound to the power d, the dimension of the manifold, halves. And then I have some constant here that depends only on the manifold, but not on the dimension, right? It depends on the geometry of the manifolds. But this is nice, because then I can truncate the functions, right? I take any function on L2, and then I can write it as a sum of some coefficients times the corresponding eigenfunctions of the Laplace-Beltrami operator, and I have an expansion there. But then I can order everything using this, and I can truncate the sum and say, okay, this function is approximately this one. Okay, and then I can, that's my Fourier analysis. Some examples, and I really pick the examples that we know, because for most of them, eigenfunctions are not at all explicit. Even the operator is not explicit at all, right? But for the sphere, we have the spherical harmonics, also appear on Dima's talk. And for the torus, we have these exponential functions that are really nice, and they look like this on the torus. So those are low-degree spherical harmonics on the sphere, eigenfunctions on the Laplace-Beltrami operator on the torus. Perfect. So now let's go back to this theory of the terminantal point process using Mackey-Shosnikov theorem and try to use these particular eigenspaces. So first we bound the value of the eigenvalues we are considering, and we know there is a number of them that we can control using Weil's law, right? So there is a number of eigenvalues here, and then I consider the associated eigenfunctions, and then I take the space span by this. Okay, that's the eigenspace, and I know the dimension of this. I can compute the dimension of this eigenspace. Okay, I wrote it a bit informal, but it captures the Lobel geometry of the manifold, right? We agree on that. And then we can think of the projection kernel of L2 into this particular subspace, and we have a determinantal point process. Actually, we have a sequence of determinantal point process, because then I can take different values for lambda, right? And I get lambda equal to the natural numbers or whatever you want, and then I will have a sequence of eigenvalues, a sequence of eigenspaces of a known dimension, and then I will have a sequence of determinantal point processes associated to every single kernel. And that will allow us to do some computations with the discrepancy, because remember, for discrepancy, I need a sequence of configurations of points, not just one configuration of points. All right, so we wrote everything down. Here, I'm missing an L2, of course, right? L2 of M can be decomposed of a direct sum of these eigenspaces, and then this is exactly what I just told in the previous slide. Everything here works well, we have a direct sum, and then I can consider the reproducing kernel of every single one. And I'm going to call this projection kernel, I'm going to denote it by K of H. And this is going to be the sum of the every single one of this K of tau is going to be an eigenspace associated to an eigenvalue. Okay? And then I sum over all of the different eigenvalues bounded by some number. Okay, so this has been done, and this is what I call the harmonic ensemble. And you can, of course, you can repeat it in every single compact manifold, because you will always have some spectrum of the Laplace-Beltrami operator, and then you will have some points that are naturally well distributed. This has been done for spheres of dimension d. This is a work by Beltrán, Marzo, and Ortega Cerdá, and they wrote explicitly the formulas for the kernel on these cases. It has been done for projective spaces, Anderson, Doster, Grabner, Mafke, and Stepaniuk. On the flat torus, Marzo and Ortega Cerdá, and recently, with my PhD student, we made it for the Grassmannian manifold 2,4. So for all of those cases, we have explicit expressions for the eigenfunctions, and we have explicit expressions for the kernel. And one doesn't imply the other. Okay, you can have a really nice formula of assumption of some orthogonal polynomials and still not to know what to do with it. But they have closed formulas for the kernels. In the case of the Riesz energy, again, we can compute everything here. And this has been done for all the spaces I have mentioned above. So spheres, projective spaces, the Grassmannian and the flat torus. Since we have a concrete expression for the kernel, then we just have to plug in here the expression. Most of the times, we are not able to compute this integral, but at least we can bound it. And surprisingly, when one does these computations and compute the expected Riesz energy of this harmonic ensemble on the different spaces, one obtains the best bounds that are known for the energy. Okay, so even though we are computing an expectation value, they give us the lowest known energy for all of those cases. But in the case that the manifold we are working with admit a complex structure. So if we have, apart from the real structure, we have a complex structure, then this harmonic ensemble is not given the best. We have other random point processes that give us smallest energy using the complex structure. And the first case is the sphere of dimension 2. That, of course, is the Riemann sphere, so it has a complex structure. All right. And for the discrepancy, again, the definition. Something has been done, and something has been done on spheres, but this is because we have a deep, deep knowledge of what's going on with the spherical harmonics. Okay, and then we have a lot of summation formulas for Gegenbauer polynomials. We know the asymptotics. We know the asymptotics and the way spherical harmonics behaves with high degree, and that's why something was done on the spheres by Beltrán, Marzo, and Ortega Cerdá, and the same happened on the torus. This is more recent by Borda, Grabner, and Matzke, and this is not done for the supremum discrepancy, as the one that I gave you, that is written here, but you have to erase the supremum and think of the L2 discrepancy. And then you can use this Stolarski invariance principle, and then it's an energy problem instead of a discrepancy problem. But those people were able to work there. Okay, so some extra ongoing work is, well, together with these people, we are doing the discrepancy of this harmonic ensemble on any 2-point homogeneous spaces. That's we recover the result on the sphere, and we can work also on projective spaces. 2-point homogeneous spaces, if you're not familiar with them, you just think of really easy manifolds that have the property that if you take 2 points and then you measure the distance between these 2 points, then there exists an isometry on the isometric group acting on the manifold that moves these 2 points into any other pair of points whose distance is the same. This is a 2-point homogeneous space, right? Of course, the sphere is, because we can always find an isometry moving 2 points. But then if we go to the torus or the Grassmannian, this is no longer the case. Okay? It's just, so there is a recapitulation of 2 points homogeneous spaces, spheres, projective spaces on the real, over the reals, the complex, the quaternions, and the only case of projective spaces on the octonions, that is the Cayley plane. So in all of these places, we can mimic this thing, and we obtain the discrepancy, an upper bound for the discrepancy. Further directions that are needed to be explored. Okay, the first one is somehow philosophical, or at least it has to be stated properly. That is how good a determinantal point process can be in terms of energy. Because for any energy on a compact manifold, any Riesz energy, we will have a minimizer. We will have a minima of the energy. And then how good determinantal point processes can be. How far are they from this perfect minimal energy, right? if they are. Or can they reach? I think no, right? But how good they are. Of course, this that has been done on compact manifolds, because otherwise we will just go with the points to infinity and this will be perfect distribution. But if we add some external fields, then all of this could be done also for non-compact manifolds with external fields. There is a lot of place to work there. And then, and again, this is just in case you are familiar with this, when working with random matrix theory, there are the so-called beta ensembles. And determinantal point processes are a very particular case of beta ensembles for beta equal 2. But for different values of delta, of beta, we obtain other type of points, and this is completely unexplored, right? So which part of the theory can be extended? Take-home messages. Okay, I hope the first one is not a take-home message, but you know that Laplace-Beltrami eigenfunctions produce geometry-aware kernels. Then the second one may be new. Determinantal point processes sample nice points on almost any compact manifold. And then we have a lot of applications. Okay, so that's all I wanted to say. Thank you very much.